Good evening, everyone. So let us wait for some 2-3 minutes so the other people also can join so that we can start the session. Okay, okay. Let us start the session. Meanwhile, people can join. So, good evening, everyone. I hope I am audible to everyone.
Yes, sir. Good evening, sir.
Yes,
Yeah, thank you. So, my name is Rakesh. I am a doctoral student at IIT Bombay. So, I am one of the TA for this manufacturing process casting and joining courses, which is taught by Sonu Kumar Chaudhary from IIT Kanpur. This is the session 2. So, session 1 was already done in the last week and was uploaded to YouTube. So, if anyone absent, you can go and watch through. So, before proceeding further, so is there any doubts regarding the last week session? Or something which is not clarified in the last live session, we can ask now. Otherwise, we can proceed. Any doubts from the last session? Okay, it looks like everyone is clearly understood. So let us move to today's session. So you are aware that there are total 2 sessions being taken. One is at Saturday, this Saturday, and one more will be on next Monday. So there are total some 10 questions in assignments, 10-15 questions. So some part will be covered by me and some other part will be covered by the other TA. So you can ask questions regarding everything, but very few questions will be solved in this session and as well as that session, so that it will be interesting for you to watch both the things. So now, before going to the practice questions, so I will show you, I will just recap some of the concept that is being taught in this week. So there are total 10 lectures till now completed. So this week from 6 to 10 numbered lectures were completed. So these are the main topics that was covered in this session. So one was the aspiration effect, which some part was taught in the last week and some that continuation is done in this week. So next one is filling time calculations. In both top and bottom gating systems, filling times. Then the third one is the optimum riser design. So in this design, so in the lecture, only that side riser was calculated, not the top riser. So we have two types, top and side one. So the calculations whatever is done is for the side riser. So and then the solidification, which is very interesting topic nowadays, how the metal solidifies in metals as well as in alloys, and what happens during the solidification of alloys. Then come to the solidification time. So this Converse rule was taught, and what is the relation between volume of the casting and the surface area. So that is being discussed in solidification time. And then finally the shrinkage, how to overcome this shrinkage and why shrinkage happens, and all these shrinkages, what are the types of shrinkages and how to avoid them. So that is being taught in this topic. So regarding these concepts, before proceeding, any small doubts regarding these things, or else you can ask me at the end. So I will continue. So these topics, some of the topics I will discuss while discussing the questions also. So these questions I will discuss, I will ask you. So I want to be more interactive this session. So if you are interested, you can like I will ask. So in first question, if I ask, so the total solidification time is defined as. So most of you has attended the lectures. So just give me. You can write in the chat box like which option is correct, A, B, C, D. So the option A is like time between pouring and completion of solidification. Option B is time between pouring and cooling to room temperature. Option C is time between solidification and cooling to room temperature. And D is time to give up the heat of fusion. So I would like to you to answer this question so that it will be more interactive, and I can clarify if there is a misconception regarding this. So what do you think, which option is correct?
Answer B, sir.
Okay, so one of the viewers says option B is correct. So any other options you can write in chat box, or you can speak out. So we have so many people. I want to answer. I got only one answer from you guys. Just whatever comes to your mind, just give it so that I can explain you very well. So what is exactly the total solidification time? So no guesses? Any guess? Okay. So I will not tell directly the answer. So I will show you what exactly happening during solidification, so that you can make out what is the answer. So if I draw the temperature time profile, say I am taking pure metal in this case. Okay, say this is the melting point. So this region is liquidus, means it is in liquid state, and this is in solid. And it will go to the room temperature, T2 and so on. So what exactly the concept of solidification? So what happens during solidification? Simply the liquid it convert into solid, that is in very simple terms. So it can happen that there are so many models we can do how liquid is solidifying. So there are some dendritic growth, all columnar growth. So when you pour a metal into any mold cavity, so the mold is at very low temperature, so that the solidification starts from the molds and it will proceed to the center. So now if I pour at this point A, I have poured the metal, and at point B I got the solid structure already, and at point C I got the solid at room temperature. So here I am not giving the scale. It is so much. It is not. If I say so, T1, T2, T3, to reach this room temperature, the time is very, very high. So now finally coming to the answer. So solidification is happening only in this region. So the liquid is being at point A, it started, and at point B the solidification has completed. So there is no any further solidification. It is the only solid that is cooling down. Hello? Any doubt? Okay, sir, please explain me Hindi. Actually, I am not very good at Hindi. Sorry for that. But I am speaking very simple English only. Just make it out. Sorry for that. So now coming to the options. So the first option is like the time between pouring and complete solidification. So this is the correct option, because it is the time between point A and point B. So now coming to the second option, time between pouring and cooling to the room temperature. So when it comes to room temperature, there is no solidification happening between point B and C. So if you see at point B and C, where there is no solidification happening. Solidification is stopped when the complete solid is formed. Of course, the temperature is not the room temperature. It might be below the nucleation temperature. Suppose if I take any, I am taking some example. So if I take aluminium, so the melting point is around 660 degrees. Taking pure aluminium. So if I take any alloy, it might be even lower, so it might be 650 also. Now this is the melting temperature. So the pouring temperature I can take some 30 degrees, so 690 degrees I am pouring it, and melting temperature is 60 degrees, where it starts forming the solid part. So this is the only difference. So now what happens, I can get a solid block, aluminium solid block, which is at 660 degrees, but it is solid. Means what is happening, even the temperature is 60 degrees. Say I should not take 60, say some 650 degrees. So it is very hot, red hot, but still it is a solid. But solidification has completed in it. So that is what the time we have to take. We should not take the time for it to become to room temperature. So the correct option is option A, not the option B. So there are other options. Time between solidification and cooling to room temperature, which is wrong. Time to give up the heat of fusion, which is wrong. So the total time is, it starts from pouring until the complete solidification. It doesn't bother about the temperature of the block. What happens is that once it reaches this temperature, solid temperature, we will just break the mold and take the part out and cool it. So we doesn't bother about coming to room temperature. So that's some detailed explanation on first question. So the second question. So in sand casting mold, the volume to area ratio. Yeah, any questions? Yeah, solidification time depends on quantity, correct? So what is the doubt in it? So bigger casting takes more time, smaller casting takes less time. That is true.
Okay, sir. Thank you.
Yeah, thanks. So now, so it also depends upon volume and area also. So in a sand casting mold, the volume to area ratio of a riser related to the volume to area ratio of casting itself should be. So I want to answer you guys. So just it is, they are asking volume to area ratio of a riser and volume to area ratio of a casting. What is the relation? Whether they are equal, they are greater than or smaller, or greater than or equal to, or smaller than or equal to. So what do you guys think the answer is? Just you can type in chat box. So I think the options are visible: equal, greater than or equal, greater, smaller or equal, or smaller. So in simple words, volume to area ratio of riser what is this thing. So in general, okay, there are some options. So it should be greater, the second option is equal, third option is greater or equal, so one more option is greater. Okay, okay, so anyone want to answer? So there are more votes to greater. Yeah,
Sir, greater is correct.
yeah, I will answer that. Yeah, so okay, I will answer this question. So now what happens? So the main, so you know the main purpose of riser is to freeze at the end, so that if there is any need for the shrinkage, so that the liquid can flow into the casting and it will fill the shrinkage. So we have this liquid shrinkage, so we should need some metal to be in liquid state, so that will be contributed by riser. So riser should be the last one to solidify. So that is the main goal of riser. So some of the options are correct. It is greater, it is not greater or equal, it should be greater, otherwise it will solidify along with the casting. No, it should solidify after the casting is solidified. So what exactly here is happening is that volume to area ratio is like, volume is saying how much heat content I can hold, and area is saying how much heat transfer. So if the surface area is more, the heat will be diffusing very faster, and if the volume is very high, we have so much of heat content in it. So the heat content is more if the volume is more. So if you take this ratio, if the ratio is higher, so what is happening? The heat transfer area is lower, so that heat transfer is lower. So what is happening? It can stay in liquid form for the more time. Suppose it is less, sorry, I said the other way. So if the surface area is more, so area, so if the surface area is less, forget this, if the surface area is less, so this total value V by A will be more. Similarly, if I take area, if the surface area is more, the total value will be less. So I think you are getting my point. So if the surface area is more, keeping the volume same, I'm not changing volume, because for this case I'm not changing the volume, just to explain you. So if the surface area is more, the value is becoming less. So what is happening is that the heat transfer is more in this case, so that it cannot stay in liquid form for more time. If the surface area is less, what is happening? That heat transfer is less, so that it can hold the heat content more time, and it will be in the liquid state for more time. So that is what we need in riser. So this ratio of riser should be greater. It should not be equal, it should not be less, it should be greater. I hope everyone is clear with this. Any doubts you can ask me now. So there was one person who answered B, greater or equal. No, it should not be equal, because if it is equal, the main goal of using razor is lost. So both will be solidifying at the same time, but we need razor to solidify at the end, so it should be greater. Option C is the correct answer. So any doubt in question number 2? Okay, so there are no doubts. I'm moving to the next question. So in this session there are only total 5 questions, so you can ask me any doubt in between. Even if you feel this is very small doubt, you can ask me, I can clear it out. So the next question: the quantity of gas that can be aspired into the molten metal stream depends on. So to answer this question, you should have the knowledge of this aspiration effect and design of that sprue. So before I explain same, I would like to answer you guys. Just answer question number 3. So what is asking that the quantity of gas that is being aspired into the molten is depends upon. The first one is the length of the sprue. The second one is the product of sprue length and metal density. The third one is length and diameter ratio of the sprue. And the fourth one is the flow velocity of the molten metal. Just put your answer in the chat box. So I'm asking question number 3. So the quantity of gas that is being aspired into the molten metal stream depends on. So the option A is the length of the sprue. Option B is the product of sprue length and metal density. Option C is length and diameter ratio of the sprue. And option D is the flow velocity of the molten metal. So what do you think, which option is responsible for the quantity of gas that is being aspired into the molten metal? Any guesses? No. Okay. I'll just explain this concept also. So this aspiration effect is very key, plays an important role. So if you see my last session, so I have explained the derivation of all this aspiration effect. So if you are, so there is finally one answer, option D, which is the flow velocity of the molten metal. No, it's not the correct answer. Okay, let me explain. So what is they are asking is that, so I have a taper sprue and I have a mold cavity, say casting I can say. So now when I'm pouring the metal inside, so we know that if I don't design this sprue, if I design this sprue in cylindrical, so when the metal enters, so there is some gap here, air pockets, where the so this happens only in permeable molds, in which the air can go inside. The air will go inside, and finally it ends up in casting as the entrapped air or casting defects, or else it will react with the mold metal and it forms some precipitates. So now the question is like this: if suppose aspiration is happening, so I took a cylindrical razor, so aspiration is happening. So if at all aspiration is happening, so the gas, how much gas it is going, and on what factors it depends. So the mass of our say mass or say volume will be nice. So volume of gas, whatever, it depends on what. So that is the question that is being asked. So this question, if I take so I directly took the sprue here, so there will be a pouring basin on the top. So there will be, so 0.1, so 0.2, so 0.3. So this is the the gate area, you can say, or the end of the sprue, and this is the starting of the sprue, and this is the starting of the pouring basin. So now if you derive, so this is the total height of the sprue. Now what happens is that if you apply this Bernoulli's principle between point 2 and 3, so you can get a equation this is the final equation you get. So the pressure at point 2 is equal to pressure at 3 minus metal density into height of the sprue. This is the final equation. So now if you see, so if I take point P3 as atmospheric pressure, so what happens? This term will get 0. So now the pressure at 2 is equal to minus rho into HT. So this is negative pressure because the sign indicates negative here. So it is depend upon the density of the metal as well as height of the sprue. If the pressure, so now what is my main point in this, that so this pressure at point 2, it depends upon the metal density as well as the height of the sprue. So if the suppose if I want the pressure to be atmospheric, this term should be 0. So now if so finally what is I'm saying that the pressure, so the amount of gas that is being entrapped into these places, it depends upon pressure 2. So this pressure 2 is related as the density of metal as well as the height of the sprue. So the final question here is that on what factors this gas entrapment is depend upon. So the correct option will be like the product of sprue length and the metal density. So it is option B. Yeah, someone answered it as correct. Option B is the correct answer. So any doubt in this? Yeah, I will keep like this. Yeah.
No, sir.
Yeah, thanks. So I hope this is clear. So I will quickly move to question number 4. So now, so that is the complete, the third question is like completely test you on the aspiration effect. So I'm moving to next question. If any doubts, you can ask me in between. No issues. So now, the riser design is considered to be optimum when. So this derivation was done in class. So I hope everyone understood. So this was the the result of the derivation. So the riser design is considered to be optimum when. So the option is its volume to area ratio is 1. It is conically designed. Its height to diameter ratio is more than 1. Its height to diameter is equal to 1. So I would like to you guys answer this question. So please answer question number 4. It asks test your knowledge on riser design for an optimum value. So I am getting answer B, 1. It's conically designed. So any other answers? So one more answer, it's conically designed. So see, it is not asking you about riser, it is sprue, it is asking about riser design. Okay. Again, it's conically designed. So there are so many like thinking that it's conically designed. So let me say this option B is wrong. Now think which option would be the correct one. So there was one answer. Its height to diameter ratio is equal to 1. Okay, let it be. So one person answered this one. So any other guesses? What is the optimum ratio for a riser design? Option A, there is one option. One vote for option A. Its volume to area ratio is 1. Sorry, there are 2 votes. Any other? So only one option is left, option C. Okay. Yeah, that's it. Let me explain this then. So now, so why I said this option B is wrong is that we are not bothered about the design. So we are here, the riser design is considered to be optimum when, so riser is something which should be solidified at the end. So that is the main goal of riser, and we never see any design for that riser, means whether it should be conical or it should be cylindrical. We doesn't bother, because even if there is any aspiration effect, it is open to atmosphere, the gas will escape easily. So the riser shape doesn't matter. So this is wrong. It can be most of the risers are like cylindrical risers, to be frank, because we don't bother about getting any defects in the riser, because that is the fluid enter finally into the risers, and if there is any gas in the casting, those gases will also go into the riser, and riser will, from there it will escape to atmosphere. The first one option is its volume to area ratio 1. So volume to area ratio, so actually this volume to area ratio of riser, it depends on volume to area ratio of casting. So this constant K generally is like greater than or equal to 2 or 3. So this constant also we call as there was one more design for riser, modulus design, that will be taught in coming classes. So it will be greater than 2, so it is not equal to 1. So the option is wrong. So now coming to option C, its height to diameter ratio is more than 1. So this is where we have to think greater than, and finally the option D is that equal to 1. So now if you do, there was very good derivation done in the class. So what happens is that if you take a volume of the riser, so I am taking in this case the side riser. So if this is casting, I am not drawing the, okay, let me draw the sprue also. So we have a side riser. So this is riser. So I am taking cylindrical riser. So it doesn't bother about the shape, just simplicity. Cylindrical riser of say some height h and some diameter d. So now if I take volume, this is the volume, and if I take area, this is the area. So we have, sorry, there are 2. So we have 2 bottom and top, so 2 into pi by 4 d square into plus pi dh is the surface area, the lateral surface area, and top and bottom area. So the finally it will be like, so this is the volume and area. So now we need to get the optimum design for this. So what you have to do is that, so we know that for riser that V by area ratio should be high, because we need it to be solidified at the end. So what we have to do is that we have to derive this area with respect to any with respect to some ratio. That ratio is d by h ratio. Okay. So this, if you derive this area with respect to this ratio r, so you will end up getting 0, then you will end up getting r as 1. So if you are very interested in how we are getting r as 1, I strongly advise you to go to that lecture and see. So it was very nice derivation. So we'll get from volume, we'll take one small relation, then we'll substitute that relation in this, and finally we'll get the value. So that is like the final goal of this riser design. So the ratio r is equal to 1. That implies that d by h ratio should be equal to 1. So here this is side riser, or else you can look whether I'm a little doubt about whether they are doing for side. So in the question they did not ask you about any side or top riser. So we have two risers. So one is, this is the side riser, and top riser will be like this, directly attached to the, so this is side riser and this is the top riser. I hope you understand. It is on the, sitting on the top directly. So what happens is that we have only this is the area that is exposed and the lateral surface area, that is pi dh. We don't have one surface here. The bottom is not there because it is into the casting. So we have less surface area in top riser. So I would like to ask one more question. If you think side riser and top riser, which one do you think more useful? So just answer yourself. I don't want to give this question for poll. So which would be better? So basic function of this riser is to solidify at the end. So which riser? The side riser should I use or the top riser should I use? So it is simple, the area calculation, surface area calculation, whichever is low, that is preferred. Yeah, any
side ratio, side riser.
So you feel side riser is best?
Yeah.
So can I ask why?
So that is, the area is higher than this top riser.
So we don't want area more, na? If the area is more, there will be more heat transfer, so it will solidify faster.
No. V by area, V by A is equal to high and A is less. Correct. Yes, sir.
Okay.
V by ratio is high. It should be high for riser. So that means area should be less.
Yes,
okay.
yes. Yeah.
So that means top riser is good.
Yeah, correct answer. Yeah, thanks.
Right. One more thing.
Yes.
One more question I want to know, sir.
Yeah, sure.
So you are told that area and diameter and height should be same for riser.
Yes.
Correct.
It depends. Actually, this derivation
No.
is.
You are telling this d by h is equal to 1.
Yes.
That is the derivation you are given.
Yes.
D by h equal to 1. That means the diameter is equal to height.
Correct.
Diameter equal to height. That
Yes.
means you have to give the riser height according to the diameter of the riser.
Yes.
So we need to give for more volume of castings. We need to give very big diameter riser.
Yes.
Is it advisable to give more high diameter riser?
Okay. Yeah, I understood your question. So basically, so I want to. So basically, this question it is asking a riser design is considered to be optimum when. So they are not specifying which riser, first of all, whether it is top riser or side riser. But what happened is that in the classes only one derivation is done, in which which is side riser, in which we got d by h as 1. So what happens there is, if you derive some other, so I'm little concerned about the whether this is done for side riser and or top riser, but let us say this is done for side riser. So we have one more derivation in which we will get 2. Say this is top riser. I'm not sure whether the derivation is done for side riser. So in this case, if you see, height is d by 2. So you are asking, so for large castings, if the diameter is big, so is it advisable to keep the height of the riser that much? So in that case, you can use top riser, so in which the height is half the diameter.
Yeah, it's correct, sir.
Yeah. Okay.
So what? Which option we to select now?
So now, so
Is equal to 1.
yeah, it's
d
simple.
by h is equal to 1.
Yeah, because that is the only derivation that was done in class. If you like,
Okay.
if you see, means if you see the class. So according to the class, these questions were framed.
Okay.
But
okay,
in
okay.
general, if any question they ask in any competitive exams, they will specify clearly side riser or top riser.
Okay.
Yeah.
Thank you. Thank you.
I hope everyone, I don't think everyone is clear this concept. Someone might be clear, someone got confused. Earlier they were clear, they thought, but they got confused, I think. So we have two types of risers. The concept is same. We take the volume and we take the area, and we minimize the area so that we will get the ratio of R. So in this question, it is very simple. So in the classes we have designed only one riser derivation was done, in which h by d ratio is equal to 1. So according to that, the option D is correct. The h by d ratio is equal to 1. So suppose there are two derivations done in class, then option C is correct. Height to diameter is more than 1, and it should be equal to 1 also, because they are not specifying which riser, na? So that's why this option will not be true, because they have to say more than or equal to. Then only this option will be, C will be correct. Otherwise D is the correct answer, the most appropriate answer for this question. Any doubts?
No, sir.
Yeah.
Carry on.
Yeah, thank you. I hope everyone is cleared. So the derivation is very simple. You can try it so that you will never forget these values. So finally, I would like to end with one small numerical, so which is based upon the earlier question. So that is, a riser of a cylindrical shape with radius 20 mm has been designed for a sand mold casting process. The optimum volume of the riser in centimeter cube will be. So these type of questions seems very easy, and people hurry what they will do in any exams. So they see this value of 20 mm, and if they remember the value of, say, h by d ratio is equal to 1, so immediately what they will do, volume is equal to pi 4 d square h, that is, since we have d equal to h, so pi by 4 d cube. So this is the formula. So simply they will do pi by 4 into, so diameter is given 20 cube, so we will get some value in mm cube, and we will give the directly answer, and we proceed to the next question. But what we have to see is that in which unit they are asking. So that is, the concept is okay, but this is more important while answering these numerical type questions, because the radius is given and it is given in mm, and finally they are asking you in centimeter cube. So it is not diameter, it is radius, and it is given not in centimeter, it is in mm. So let us calculate everything in centimeters to avoid that confusion. So the everything is same. So the volume is equal to pi by 4 d cube, assuming the h by d ratio 1, because we taught that in class, nothing else we taught. So h by d is equal to 1. So pi by 4. So now diameter we need, which is 2 times radius, that is 2 into 20 whole cube. So we need it in centimeter square, so I am keeping 2.0. So finally the answer is like whole cube, that is 16 pi. So if you have calculators, just calculate this value 16 pi, how much it is given. Just put the answer in chat once. Yeah, correct. That is answer is 15.26 centimeter cube. So whenever you see these type of questions, yeah, correct. Yeah, I'm very happy so many people are doing calculations. So whenever you see these simple questions, don't make mistakes in seeing the values, what units they are asking and what the values, the units of values they are giving. So this is where they play with the these numerical questions. So with this I would like to end. I would like to allow to the users to ask any questions if they have. Yes. Some people joined just now, so don't worry, this video will be uploaded, but I suggest strongly to join early so that we will have some good conversation. So if you have any doubts you can ask, otherwise you can carry out this your usual work, and happy weekend.
Hello, sir.
Yeah.
Sir, another 5 questions when we discuss
So
next
the next 5
Saturday.
questions. So there was one more TA, Balaji. He is from NIT Trichy. He will teach on next Monday.
Okay,
Yeah.
okay.
So that it will be interesting for the viewers also, because if I solve every 10 questions and even he solves every 10 questions, it will be boring. So that we shared these questions, so it will be interesting for you guys.
Okay, thank you, sir.
Okay, yeah, thank you.
Sir,
Yeah.
sir, please show first and second question, sir.
Okay. These questions?
Yes, sir.
Do you have any doubt, or just shall I read it out?
Sir, nothing doubts, sir.
Okay. So I'll just explain you in very brief way. So the first question is asking about what is the total solidification time. If you learn this concept of this temperature versus time curve, so what is happening? So we are getting, so at point A we are pouring the temperature. So above point A, so this is Tp. Say I'm pouring temperature at here from this point. Okay, point A, and at point B I'm getting solid, red hot solid. So the solid, the metal has become solid, but the temperature is still around, say, some 500 degrees Celsius. So this pouring, say I'm taking 66 degrees Celsius. I'm giving values, just you can visualize. It is still red hot. It is 500 degrees Celsius, but it is solid in state. So from that it will cool to room temperature, say 30 degrees Celsius. So now the question is, what is the solidification time? So it is the time between the pouring and becoming it is a solid. So if you see option A, time between pouring and complete solidification, that is the correct option. So the other options is like time between pouring to room temperature. So we will never come to, the solidification happens before room temperature. When it becomes completely solid, there is nothing to solidify. So what happens during solidification? These grains will develop, the dendrites will form, and they will occupy complete structure, and it becomes the solid part. The second question is asking about V-by ratio of riser and V-by ratio of casting. So I am repeating this thing every time, but it is of that important. The riser, we design riser so that it solidify at the end. So the volume to area ratio of the riser should be more. So if it is more, what happens? The heat content in the riser will be more, so that it will stay in liquid state for more time. So the V-by ratio should be greater than casting. So option C is the correct answer in this. I hope I cleared. Yeah.
Yes, sir. Thank you, sir.
Yeah. Thanks.
Sir, total solidification time depends on quantity. So here quantity means area and volume, right?
Yes. Yes.
Okay, sir.
So just to add to that, so if you see solidification time formula, that Carnivor's formula, so total solidification is some mole constant into volume by area whole square. So now it will be, say, I am taking in minutes. So the solidification time is completely depend upon volume by area of casting. It's not only volume, also area. That ratio we have to take into consideration. So any other doubts?
No, sir.
Okay. Yeah. Thank you. You can leave if there are no doubts, and you can carry on. You can meet in next session.
Thank you, sir.
Yeah. Thank you. Thank you for attending.
Thank you, sir.
Yes.
Good evening, sir.
Yeah. Thank you.
Thank you, sir.
Thank you. Yeah. Thank you.
Thanks, sir.